In carbon capture and storage, three geologic factors, storage capacity, injectivity, and containment, serve as the foundation for determining whether a subsurface formation is suitable for long-term CO2 sequestration. These parameters are closely interlinked and must be thoroughly evaluated to ensure that storage projects are both technically feasible and environmentally secure. Storage capacity refers to the total volume of CO2 that a geologic formation can safely and permanently hold. This capacity depends on several factors, including the porosity of the reservoir rock, pore space saturation limits, reservoir thickness, and areal extent. An accurate estimation of storage capacity helps in understanding the scale of a project, selecting appropriate storage sites, and ensuring long-term economic viability. However, having sufficient capacity alone is not enough. Injectivity is the measure of how easily CO2 can be injected into a reservoir at a practical rate without exceeding pressure limits that could compromise the integrity of the formation. It is governed primarily by permeability, reservoir pressure, fluid viscosity, and geomechanical properties. High injectivity is essential to accommodate large volumes of CO2 within a reasonable operational timeframe, especially for large-scale industrial emitters. Low injectivity can result in increased costs due to slower injection rates, the need for more injection wells, or even operational risks related to pressure buildup. Moreover, a reservoir's injectivity must be compatible with caprock integrity and fault stability to avoid unintended migration pathways. Containment, perhaps the most critical parameter, refers to the ability of the geologic system to retain CO2 over long time scales without leakage. This includes both physical containment, typically provided by an impermeable caprock or seal, and geochemical containment, which involves CO2 reacting with reservoir fluids and minerals to form stable compounds. Ideal containment systems consist of multiple trapping mechanisms, such as structural, residual, solubility, and mineral trapping, which act at different temporal and spatial scales to immobilize CO2. Evaluating containment also involves monitoring the integrity of faults and fractures, assessing capillary entry pressure of the sealing rocks, and modeling pressure propagation throughout the reservoir. Together, these three factors form a comprehensive framework for evaluating CCS site suitability. A site with high capacity but poor injectivity or weak containment may not be viable, while a moderately sized reservoir with excellent injectivity and secure containment might offer a more dependable long-term solution. Advanced site characterization techniques such as seismic imaging, well logging, pressure and flow testing, and geochemical analysis are crucial for accurately quantifying these parameters. As the demand for large-scale CCS deployment grows, understanding and optimizing storage capacity, injectivity, and containment will be central to ensuring both the technical success and public confidence in carbon sequestration projects.